Okay, so find the distance from point Q, the point to a plane. So, I don't know if I'm going to show you the answer. I could draw, is it still frozen? I could draw a picture, because I'm pretty sure I don't have a picture in my answer. Let me unfreeze. Let me show the solution first. Let's just check and see how we did. All right, so I got 18 over root 14. Match, 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 match. Yes, yes. All right, 100%. Well done. All right, so let's, yes?
Would you like to draw a picture to like show like the projection of the point?
Yes, absolutely. So many of you guys did the formula, which is fine. So, oh, wow. Did I do a formula here?
Yeah.
Oh my goodness. Okay. I'm gonna walk through it and just see. Okay. So you have a distance from a point to a plane. So you have some point Q, and we have some plane, right? So we know the vector orthogonal to the plane. Let's just put it there, right? So this vector right here is 2, -1, 3, and we just pull that out of the equation of the plane, right? We need a point on the plane. So to pick a point on the plane, any point that makes that work is a point on the plane, right? So I used 0, 0, 4. You could have used 6, 0, 0, right? Any point that works is on the plane. So we have some point on the plane. I'm going to put that there. So this is P. This is Q. This is our vector orthogonal to the plane. So we have vector PQ. We have this vector N, which is the one orthogonal to the plane. The distance from the point to the plane is just the magnitude of the projection of PQ onto N, because this distance right here is the same as this distance right here. Like, it's the perpendicular distance from the point to the plane. Right, I gotta close this over. So, oh, okay, and so no, I did it using projections. I just didn't call it a projection. So the magnitude of a projection, remember, it's just the dot product over the magnitude of your like if I was doing, here, let me write this out. Is this all one? It is. So if I did the magnitude of the projection of PQ onto N, what is that? It's PQ dot N over the magnitude of N. Right? That's the magnitude of the projection is just the dot product over the magnitude of the lower one. And then the magnitude of the projection in this case is your distance. So that's how I did it. So yeah, see, this is not the formula, but it's the same as the formula. Like it's funny because it looks like it because the numbers you have in the formula are the same as the numbers that I have in the dot product. So anyway, but yeah, so that's how does that answer your question, Tejesh?
Nope.
Okay. All right. Find the distance from the point to the line. Again, this is that cross product formula. If you want to use the cross product formula, I do not. I just don't learn those. Someday I'll learn those formulas. So, sorry, those of you who are watching, I'm going to erase this just so I can move this stuff over and get it out of the way. Moving back over. All right, so when you have a distance from a point to a line, so you have, let's pretend that's our line, and let's pretend that's our point. All right, so we have some point out in space. That's the 4, 1, -2. And then we have some line. So we pick any point on the line. I'll put it over here. So that's point P. Point Q we'll call the point that's out there in space. So the point on the line, how did I get it? I just used it from the equation, right? So 2, 0, -1. Again, any combination that works is fine. But anyway, so I just pulled the point from the equation. So there's my point on the line. There's my point in space. So I find this vector right here. So I get -2, -1, 1 just by subtracting. Then I need the vector equation of the line. the direction vector for the line, which I'm going to point this way so it makes more sense. All right, so that vector right there, you get from your equation, right? It's 3, 2, 1, 3, 2, 1. So pretend that's the vector. I'm calling it n. All right. So now, if I do the projection of PQ onto n, I end up getting this distance, right? The magnitude of the projection of PQ onto n. Remember, it's on n, right? Literally, your projection is on the vector that you say it's on. So that projection is on n, so it's this distance right here. So this distance is 7 over root 14. This distance, I just find the length of PQ. Where did I find the length of PQ? Did I ever find the length of PQ? Let's see. Well, let's see. The length of PQ. So square root of 4 plus 1 plus 1. So root 6. So root 6. And then, so to find my actual distance, I do 7 over root 14 squared plus d squared equals root 6 squared. Solve. So that's how I do it. You know, it's so I got root 35 fourteenths, the square root of 35 fourteenths. So, or root 35 over root 14. Yes.
So we just talked about how we can subtract the points. Okay, so I subtracted points in the wrong order, and I got a different answer, and I got the wrong answer.
So you subtracted the points, but your vectors, so you got, no, it's not that you subtracted in the wrong order, it's that you have a math mistake. So, because 2 minus 4 is negative 2.
Oh.
Yeah. So, yeah. All right. Yes, John.
Did you use the formula that we did in the notes? We got a problem.
Did you use the formula correctly?
Fine.
Okay, so here, remind me what the formula is. Let's pretend I don't know the formula, right? Hypothetically, right? Okay, so formula. So distance from point to a line. Point to a line. All right. What's the formula? I'm ready.
So it's the magnitude of the cross product of the vector PQ and U.
Cross, so what I called n, or you could call u. Okay. All right.
Over the magnitude value for vector.
Okay. So if we do, so we have our PQ, negative 2, negative 1, 1, and our u, which I called n, but our u is 3, 2, 1. All right. So negative 2, negative 1, 1, and 3, 2, 1. So let's do this real quick. Okay. Negative 2, negative 1, 1, and 3, 2, 1. And this is going to be divided by the magnitude of this guy. So 9 plus 4 plus 1. So 9 plus 4 is 13, root 14. Okay. So we got the root 14 like without doing anything, right? So really what you are concerned with is the magnitude. I should put this in double so we know the magnitude. Okay, so it's the magnitude of, so negative 1 minus 2, so negative 3. Negative 2 minus 3, negative 5, but 5 because we take the opposite sign. Negative 2 plus 3 is positive 1. So let's do the magnitude of this. So you end up with 9 plus 25 plus 1 over 14, and we have square root. So end up with root 35 over 14. So let's see, what happened?
Wait. 2, 1.
Your PQ doesn't match. Why does your PQ not match? Is that number 2 where it says PQ, or is that number 1? I can't tell. That's number 2. How did you got 1, negative 1, 2? 1, negative 1, 2. Are you sure you didn't like accidentally switch your X and your Z? But it shouldn't make any difference. Do you want me to use your point? Okay, let's use your point. We'll do it again. So, all right, so you had 3, 2, 1 for this vector. So your vector PQ, so the point, let's see. So one of the points had to be 4, 1, negative 2, because that was given. You can't change that, right? Okay, so the other point you used was 5, 0, 0. 5 minus 2 is 3 over 3 is 1. 1 doesn't equal 0, which equals 1.
Oh, I would.
Yeah, so your point was just wrong.
The first equal sign was close. So I had it on that stuff.
Those are symmetric equations. Yeah. All right, there we go. All right, so mystery solved. All right, last one. What's the last one asking for? Where do the above line and plane intersect? I have not actually taught this because I just haven't. So I think it showed up though in a homework problem. I'm kind of curious. I was actually expecting people to come in and ask me about it. Nobody did, so I figured you just kind of figured it out. So if we have this plane, 2x minus y plus 3z equals 12, and we have this set of equations, what I do, and I think it's the easiest way to do it, is just rewrite your linear equations in parametric form, and that way they're all in terms of t, and then you just plug each of those, like the first one in for your x, the next one in for your y, and the next one in for your z, and you get one big equation that's all in terms of t. So here's mine. So I'm going to erase. Can I erase this stuff, or maybe I can move it down? Okay, that's fine. There. All right, so here's what I got. I said, so I rewrote my line parametrically, and then here's the plane. So all you do is you take x and plug it in for x, right? And then you take y and plug it in for y, right? And z and plug it in for z. And I'm just underway like crazy. And then you just clean it up, and you're up with your t value of 11 sevenths, and then you just plug 11 sevenths back in for t. I actually really like the equation, the point of intersection of a line and a plane. Those I think are kind of fun. They're pretty easy. Just write the line parametrically and plug it in, and then just simplify and solve. Okay. How are we doing? Today is kind of a fun day. It's a very different day. So, and the good news about today's lesson is it's not on your test at all.
Yeah.
Oh, it's like the different shapes.
This is shape day. So take a minute. I want you to, you're going to be using your laptops all day. So go ahead and grab your laptops. No, Big Quiz is Thursday.
Oh,
Yeah, tomorrow, so I was able to like update my Cal 3 calendar. I did it based on the Normandale calendar, and even like with theirs, we are able to cover all the content and get 3 review days per unit, plus a quiz day in the middle of the unit for every unit. This time we lost our quiz day because of the active classes, but normally we'll have a day in there where we just kind of catch up and work on quizzes. So anyway, yeah, so tomorrow we're going to review all day. We're going to talk about what's on your test. We're going to play a game. Then I'm going to show you all the review materials available, and then I'm going to leave it to you, and I'm just going to rotate around and help. So that's the goal for tomorrow. Thursday is your big quiz. Friday, we review again. We just go over the big quiz and answer questions, right? Do any more practice we need, and then Monday is your test. All right? Okay. So, did everyone type grapher? Do you guys have grapher up on your screen? Now, when you go to grapher, where's my grapher? I was using grapher during grapher. Where'd you go? Here it is. Okay, when you go to grapher, you pick 3D graph. Now, personally, I find a white background makes it easier to see the graph But you can change that if you want to. But I like the white background on a 3D graph. Now, your default for your equation is z equals. You can destroy that if you need to and just type right over it. But our first equation we need to graph is z equals y squared. Z equals y. So do you know how to put squared? It's the little caret above your 6. So you do like shift 6 to get the exponent, right? And then type the 2. A little note, if I had to type more after this, I have to arrow, like hit my arrow to get out of the exponent. Otherwise, I'm still typing in the exponent. So you hit your right arrow to get out of it if you need to keep typing. So when we type z equals y squared, it looks like this. All right? Hey, if you just look at it straight on, what shape does it look like? Looks like a parabola, right? Okay. Yeah, by the way, just a little word about Grapher, if you want to play with the colors. Yeah, I love that you guys are playing with the rotation, and I love that you're kind of figuring out how to zoom in and how to zoom out. If you right click or like double click or whatever, you can pick this edit appearance. And so you can turn the checkerboard off and instead have it be uniform or stripes or whatever you want. I tend to like uniform better. It's hard to see gray, so then you can change your uniform color to be, you know, whatever color you want, right? You want blended? Blended. I have no idea how this works.
Mine was like a rainbow one right away.
Oh, did it really?
Yeah.
Oh. Oh, you know what? Mine has that too. It's got kind of, oh, I like that.
Right?
Yeah. I've never used blended.
I like blended.
My computer's almost dead.
So we're going to use squared. No, if you want to graph, but if more than one equation, my second is sine x. Z equals sine x.
How can you zoom it in or out? It like what it looks like. Like it doesn't just get closer, it like changes the. Oh, I guess you get really close to the problem. You're right. It's fun.
And then once you have multiple graphs graphed, up here you see those check marks. So if I only want to look at the sine x, I can turn off the check mark on my y squared and just focus on my z equals sine x graph. All right, so if you noticed, z equals y squared has kind of like a cross section of a parabola, right? Which you would expect from a y squared kind of a graph. Z equals sine x has a cross section that basically looks like a sine graph, right? Let's switch, there we go. Let me turn it, there we go, spun it around. So anyway, it looks like a sine graph. So my question to you is, can you guess the names of both of these shapes have the same name in 3D?
Oh.
And it's a name that you're very familiar with. It's a name that you've been using for years. You guessed it. They are both cylinders.
What? What?
Okay. So you have been, you know how like each year I enjoy like telling you all the things that you've been taught in the past that were a big lie? So this is like your first big lie of the year. So you guys are used to a cylinder being like a can, right?
Yeah.
Okay. So a cylinder that's shaped like a can is technically called a circular cylinder.
Okay.
But the cylinder doesn't have to have a cross section that's a circle. A cylinder can have any cross section you want. So you can have a sine cylinder, right? Or you can have a parabolic cylinder. So here's what defines a cylinder. A cylinder is defined if you take any curve, right, in 2 space. And then, so you've got a curve in 2 space, so that means that that curve passes through 2 variables. It could be x and y, it could be y and z, it could be x and z, right? But you've got a curve in 2 space. So for all of these, the 2 space is x and y. So we've got a curve in 2 space. The cylinder, if you take all the lines, it's going to be my horrible demonstration. All right, so like if you have, just looking straight on, you see that curve, right? If I take all the lines that are perpendicular to that curve, it's a really bad demonstration, perpendicular to that curve and parallel to each other. So they have to intersect the curve, they are perpendicular to the plane that contains the curve, and they're all parallel to each other. So if you take the set of all lines that intersect the curve, they're perpendicular to the plane that contains the curve, and they're parallel to each other, you now have a cylinder. So a circular cylinder, you just have this circle, and then you have all the lines that intersect the circle, they're perpendicular to the plane that contains the circle, and they're all parallel to each other. They all have the same direction vector, right? You now have a cylinder, but it's a circular cylinder. Yes?
In this example, where's the plane that?
So this one, if you look at it straight on, whichever like 2 variables you're graphing it with, I wonder if this is the YZ plane. This is a YZ plane, right? Anyway, yeah. Now, knowing this specifically isn't that important. Let me, that's just me like, whoa, there's cylinders. Oh my goodness. Okay. So I'm going to show you the definition if you want to write it down. You don't have to memorize any of these definitions, and you don't even really have to memorize the equations or the names. But if I say something like hyperbolic paraboloid, I want you in your brain to be able to picture what I'm talking about. Because a lot of these problems get presented and they'll say the equation of the following, and they'll name the shape by a name is, and then they'll give you the equation. So you don't have to create it, but it's good if you have a general idea in your brain of what the shape looks like. So anyway, so a cylinder. So what's the definition of a cylinder? It's a set of all lines intersecting a curve C that are parallel to each other, but not parallel to the plane. So I'm trying to think of how that works. Yeah. So I guess you could have them all, they don't have to be perpendicular to the plane, because you could have them all going like this and you'd still have a cylinder. Yeah, that works. So a set of all lines parallel to each other that intersect a curve C that are not perpendicular to the plane that the curve is in. Or not parallel to the plane that the curve is in. So the equation of a cylinder is just the equation of the generating curve C. So no matter what, if you have an equation of the so the last one was in the YZ plane because it was in terms of Y and Z, yeah. Okay, so if you have a generating curve C, then when you graph it in 3 space, you automatically end up graphing the cylinder. So if we did that in the XZ plane, so say I graphed, so instead of this, let's graph x equals y cubed. Woo! Okay, so in the, I've got it flipped upside, there we go. So in the XY plane, we've got y cubed, but then on the Z axis, you've got all these parallel lines that go along, and there's your cylinder. Kind of fun. So anyway, so this is a cylinder, right? Because it's the set of all, like you've got a generating curve, and then you have the set of all lines that intersect that curve and are parallel to each other.
So what's a circular cylinder in 3D?
So a circular cylinder, so let's graph x squared plus y squared equals 9. All right. There you go. All right. Whoop. So there you go. All right, so now you know real for real what a cylinder is. Okay, so that was the first thing we needed to learn today, was to help you understand what a cylinder was. All right. Got that. Oh, by the way, those parallel lines are also called rulings. If you want to write down the word rulings, the rulings are the set of those parallel lines. All right, now it's time to get into the fun stuff. Okay, quadric surfaces. This is the main goal. You got fast.
Yeah.
Wow, we've barely started. All we do is go over the warm up and talk about cylinders. Okay. All right. Okay, so a quadric surface is any surface that fits that lovely equation. Now, just like a quadratic equation just means it's an equation with an x squared, right? A quadric surface is an equation with an x squared and or a y squared and or a z squared. You don't have to have all three. You can just have one of them, right? As long as something's being squared, you have a quadric surface. So at least one of those coefficients of an x squared needs to be a number. Yes?
So, if it was just like a number, it would be a quadric surface.
Technically, no. Because it's just gonna be a plane. Yeah. Okay, so we're going to talk about each of these quadric surfaces. Now, I need to tell you, I cannot sketch in 3D like to save my life. I can sketch a rectangular prism. Like I am a pro at sketching a box. Anything that's not a box, I'm done. So if you want to try to sketch for yourself what these look like, that's fine, but you sure don't have to. So here's what I'm going to do. The first one is called an ellipsoid, and it makes sense, right? Because it looks like what you get if the cross sections are all ellipses. Like if you take these ellipses and I don't know, kind of rotate them. So anyway, the equation of an ellipsoid should look really familiar. So x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. If you took the z squared over c squared out, what do you get? You get an ellipse, right? So an ellipsoid is just now adding a z component. So it's like an ellipse in every single direction. So now it's called an ellipsoid. All right, okay. So the next type of equation, here's the graph. What do you think this shape is called in 3D? This was called oh my gosh, I gotta say it. This is called an ellipsoid. This is called
Paraboloid?
Semi-ellipse.
I think so.
Paraboloid?
This is called a paraboloid. Now,
I am so
okay,
cool, guys.
there are different types. You didn't want to say it out loud? Oh, okay. There's no shame, right, in getting it wrong. This is new stuff, right? You're not expected to know. So there are different types of paraboloids. So this type is called an elliptic paraboloid because if you look, the cross sections are ellipses, right? Okay. Oh, and let me show you the equation.
Is there like a common form of equation for all paraboloids?
I'm going to show you the next one, and then we can see what's the same and what's different. I can tell you, I know in advance what's going to be different, but so I don't know if, well, I can tell you this. No matter what, a paraboloid will always have one variable that's not squared.
Okay.
So that kind of helps a little bit. But remember, you won't get tested on this. It's really just to kind of help. This today is just to help your brain kind of start recognizing shapes a little bit.
Do we need to like know the formulas, or is this really just to recognize?
It's really just, today is just fun with learning and fun with shapes day. Okay. All right. So this guy right here has a fun name. So this, okay, that was an elliptic paraboloid. Anyone have a guess? If we slice this, try, it's a hyperbolic paraboloid. This is called a hyperbolic paraboloid because now you got parabolas, but your cross sections, if you sliced it, would be hyperbolas. Now, this graph gets used a lot when we get into, I think it's chapter 14, when we do extrema. We will be doing like relative maxes and mins, right, and absolute maxes and mins. So this graph is really fun because of like this point right here, because if you think about it, it's like it's a max going this way and a min going this way. And so we call this, I call it, and I think your book, I don't remember if your new book calls it this or not, but I call it a saddle graph because it looks like a saddle, right? Or a Pringle, okay, looks like a Pringle. All right, I always call it a saddle graph, but anyway, so hyperbolic paraboloid, we will get into a lot in chapter 14. They're kind of fun. And I don't know if you guys remember when you did conic sections, but hyperbolas always have a minus sign. Does that kind of ring a bell? That's how I always remember them, right? So parabolas always have a variable that's not squared, right? So I don't know if you guys remember ellipses, circles, ellipses, hyperbolas, everything was squared, right? Okay. Parabolas, you always have a variable that's not squared. So an elliptic paraboloid, you have all pluses and a non-squared variable, and a hyperbolic paraboloid, you have a minus and a non-squared variable. So anyway, all right. Next shape.
Whoa.
What is, if you didn't look at the bottom and just looked at the top, what does it look like? Looks like a cone, right? Okay, so now we have what's called an elliptic cone because it doesn't have to be circular. So you can have a cone with cross sections that are ellipses. You can have a cone with cross sections that are circles. But either way, so this one's an elliptic cone. If A, B, and C are all the same, then it's a circular cone. So anyway, so that's the equation of a cone in 3 space. X squared plus y squared minus z squared equals 0. Or the way that you'll see it written a lot is x squared plus y squared equals z squared. You see that a lot. All right, so that's a cone. Okay, so you guys, so I'm glad that you see hyperbola, right? This, we've had an ellipsoid, we've had a paraboloid. It's time for a hyperboloid. Now, this is called a hyperboloid of one sheet.
What?
I will show you the difference in a moment. So again, now with a hyperboloid, everything's being squared, and you have a minus. What makes the difference between an elliptic cone and a hyperboloid is that this one you've got equal to 0, and this one you have equal to 1. So this one is more like your traditional hyperbola equation. You got that equals 1 there. All right. Last one.
Hyperboloid of 2 sheets.
This is a hyperboloid of 2 sheets. Okay, so hyperboloid, hyperboloid, you put them to like they're separated now, right? These are connected, these have space in between, and now you got double negatives. Again, there is no time at all this year that you will be tested like given an equation, what's the name, what shape is this, right? Or given a shape, write an equation, ever. It's really more for you so that if I talk about something like a paraboloid, you have an idea in your head of what I mean. Okay? But just for fun, I made a little activity. So here's what I want you to do. On your whiteboards, So I want you to use Grapher. You don't have to match them up with equations. Like use Grapher. That's fine. That's why you have Grapher, right? So I want you to graph these. I don't want you to graph them like you just on your screens. Like you don't have to actually sketch the graphs. But what I want you to do for each of these 5 is name what they are. Each of these is one of those shapes we just named. So I want you to see if you can name what each of these is, and I want them on your whiteboards. Okay, so you can each like take an equation, graph it, and then you can all decide what the names are.
I have a question.
What are you
Unrelated.
doing?
What is it? You just put that in I don't understand. Or
You didn't have, it's not an equation, you didn't put equals
Why
in.
does it do this?
I don't know, they look like molecules. I've never graphed without an equal sign.
Look at this.
We're getting the quantity.
We were trying to figure out what it was.
Some of these things you can do for the examples are crazy.
Also,
You know what it's trying to show you? It's trying to show you at each point in space that it is a dot with that whose like maybe width is the size of the x value at that point or something. Maybe.
then we're at the beginning, like different.
And then why would negative?
Negative would be 0, wouldn't it? But which way do you have yours oriented? Where's positive? Like, I gotta see. Okay, there's x, y, and then z is going up. So know that. Wait. Oh, you had it back.
Well, I'm on Z.
5 is?
Yeah.
Okay.
Negative.
So negative still has points. I don't know. You lost me. Oh, but wait, you're on Z, not
Yeah,
X.
I'm on Z.
Negative.
How do you spell paraboloid?
Why is it not every single point?
Sorry, this is totally random.
I have no idea.
Just, like, stumbled
I've never
upon
tried
this
graphing
and
like
we were
that.
confused.
So that's kind of neat.
Have you done the examples?
Have I done these?
Look, this one's a cylinder.
Oh, yeah. I had a student last year who insisted every day on having an example floating in the background of his computer. And so every day he would pull a different one, and then it would, and it would just be like his.
Do you know how that equation works?
No idea.
Do you know what these equations like are?
Well, this is just it's a vector equation, right? So we haven't gotten into vector equations yet.
What was
Real
this
nice
battle?
chapter, and then
What is all this? So,
So bad at this.
no, sorry. Alright.
All right, I'm going to pause this for a few minutes. Every single group matched. From what I see, we all matched. So the first one, let's see if you were all right. Ellipsoid, yay! Still, I didn't even put circular cylinder, but you were correct. Circular cylinder, yay! Right? So this would be a circular cylinder that would be centered about the x-axis, right? Okay. So, because the curve would be in the YZ plane. All right. This one, I messed with you because it wasn't written in standard form, right? So but you can still graph it. Have you guys realized, like, you can just back over the z equals and just type it exactly as you see it, right? Okay, you don't have to solve for z. Okay, so hyperboloid of 1 sheet. Oh, you guys said 2 sheets. Wait, did I get 1 sheet or 2 sheets? Hyperbolic paraboloid, and I just put a paraboloid. It could be, you could say elliptic paraboloid. Just so you know, if I ever just say paraboloid, I mean elliptic paraboloid. Like, you get paraboloids so often that I always just call them paraboloids. How come I got a 1 sheet? Let's graph this and make sure. If you guys all got 2 sheets, then you guys are right. I must have just typed it in wrong. So, let's see.
Oh, but if you zoom out a lot,
Okay.
this is
So,
what we got when we graphed it.
okay, let's see. Ooh, this might be a good time to talk about zooming.
Yeah.
Okay, 4x squared minus y squared plus 2z squared plus 4 equals 0. Okay, so if you look at it like this, it absolutely looks like a hyperboloid of 2 sheets. But if we zoom in, out, zoom out.
No.
Why?
No.
What? I don't
Mine is
But it's still separated.
barely.
Yeah.
It's like barely noticeable.
Well, let's just see. If we plug in, like, okay, it looks like it's centered about the origin, but 0, 0, 0 is not on the graph, right? So, I think it's 2 sheets. I think if we actually solved this correctly, somehow wrote it in standard form, it would be 2 sheets. I think you guys are right.
Wait, what's the equation for one sheet again? Like standard?
Oh, I think I was zooming out and I should have been zooming in. All right, let me get this out of here. Come on. There we go. Oh yeah, they're totally separated.
Yeah.
Yeah, it's definitely 2 sheets. Okay. So let's make sure I didn't mess up. So it says 1 sheet, and this says 2 sheets, and I'm pretty sure those are correct. So I'll have to double check and see what's up with that, because this is definitely a hyperboloid of 2 sheets. I'm looking at the graph. All right, I'll check on it. Not a big deal. Now, this last thing we're going to talk about, this is not even in your new book. It might be in your new book later on, but our old book used to talk about this in the same section. And again, you don't have to learn how to do it. You're not going to be tested on it. But there is a different type of surface. So those surfaces, do you remember what those were all called? Quadric. Quadric, not quadratic, but quadric. So those surfaces were all called quadric surfaces, where you've got, and they're all basically like 3D extensions of your conic sections, right? Now we're going to do some funky surfaces of revolution. So the neat thing about a surface of revolution, you guys did volumes by revolution last year, right? But you never learned what the actual equations were. All we would do is we would say, hey, find the volume when you revolve some equation about the y-axis or whatever, right? So what does the actual equation of a volume of revolution look like? Well, we know the cross sections are all circles, right? So in general, normally when you have an equation of a circle, you have x squared plus y squared equals r squared, where r is a constant, right? But now when you have a surface of revolution, you have x squared plus y squared equals, and this is this is your curve. So like, say we are, I'm going to show you, you can write, I don't know if you want to write this down now. Okay, so I'll show you an example and then it'll make more sense. So say we're going to write the equation of the surface generated by the curve z equals ln y, and we're revolving it about the z-axis. So whatever axis you're revolving about, that's the variable you want in here. So this is our curve of revolution right there. That's the curve we're revolving. But we want this in terms of z because we want to revolve about the z-axis. So I'm going to have x squared plus y squared equals sum r of z squared. So what threw me the first time I did this, so you solve this for y and you get y equals e to the z, right? And so you just plug that x squared plus y squared equals e to the z squared, and you get your equation. What threw me was, how come this works whether this is a y or this is an x? And then I thought, it's because these are circles. The x's and the y's are exactly the same. So it wouldn't matter if this was x equals e to the z or y equals e to the z. They're all the same because they're all sitting on this circle. So, so if we graph x squared plus y squared equals e to the 2z, let me show you what happens. So let's see. X squared plus y squared equals e to the 2z. All right, so what you get, if you look along here, this looks like the equation. Basically, it's kind of like a natural log graph, right? So, so the cross sections are all circles, right? it's basically that natural log graph revolved about the z-axis. And so it's kind of neat, right? So now you can write an equation for a surface of revolution. All right, I have one more. Okay, if we revolve the equation 2z equals the square root of 4 minus x squared about the x-axis, so whatever axis you're revolving about, that's the variable you want your equation in terms of. So we solve this in terms of x. So you get z equals 1/2 root 4 minus x squared, right? Okay, so when you get z equals 1/2 times the square root of 4 minus x squared, so you do your y squared plus z squared equals, and then you square that, you get 1/4 times 4 minus x squared, right? So think about what that equation, anyone know what the equation of the square root of 4 minus x squared looks like? It's a semicircle, right? -2 to 2, right? Okay. Anyway, so we have y squared plus z squared equals 1/4 times 4 minus x squared. So playing with that, so y squared plus z squared equals 4 minus x squared all over 4. So here's the thing. So you've got this semicircle, which, we're centered about the x-axis. So you've got this semicircle, but then what happens is your circles, as you go out from there, end up getting like smaller and smaller, and you end up with this ellipsoid shape. So kind of fun. I always think it looks like a football. Anyway. Yeah.
Why did you set it equal to y squared plus z squared?
Oh, so whenever you need a volume, or I keep wanting to say volume because that's when we teach it up. Whenever you need a surface that's based on revolution, your cross-section will always be circles because you're revolving, right? So the two variables that make up the circular cross-section, so if your circles are parallel to the YZ plane, it's going to be a y squared plus z squared. If they're parallel to the XY plane, it's going to be an x squared plus y squared kind of a thing. So your two variables are whichever ones you're using to generate the circle. And then the shape like that you're following along on that you're revolving about, right? Like, so if I'm revolving my shape and I'm revolving it about the x-axis, then so my other two variables would be y and z, and then that would be an equation in terms of x squared, or whatever I'm revolving around. I didn't explain that very well. But so like, if I'm revolving about the x-axis, then this needs to be in terms of x. So this, I can look at this and say, okay, I'm going about the x-axis. As soon as I know what I'm revolving about, then I know my other two variables are going to be the other ones, because my cross sections are going to be in the YZ plane. So then I get a y squared plus z squared, and then this is the equation that I'm revolving around the axis squared. Did that help at all? I don't know. It doesn't. You'll never be asked to do it. So in a way, like, but it's kind of, if you can follow it, it's kind of a fun thing to know. So anyway, all right. That being said, so that's all I'm going to do.